said that we're going to last time basically hit most of the proofs. So I still want to make precise the exercise last time and discuss them briefly because I think they are important for understanding the last images. So first, there is this that V is reducible, the X module, and support of V is close. And actually this exercise, the best thing to figure out how to do it is because George's example from last time and this before this this and just throw away one copy of C and then another copy of C. Look at the canonical extensions, see what's going on, and then figure out. Great. So this is one exercise.
Just to make sure this is nothing to do with D, right? Or to do with like any quasi-energy value.
Yes. Yeah. This is just what I believe. Yes, this is bad. It won't go to this is just about this. The second thing I want to discuss is the question about unions. And in a special case, this special case implies everything else with bunch of tricks, so we can play the same game. So I'll consider the case that X is n plus 1 and Y is Cn embedded in Cn plus 1 in such a way that x1 to xn goes in x1 xn sigma. We have spiritual. And then let's I this inclusion of y to x. And then if we take u to be the y module, here this dy is just global differential operators on Cn. So these are differential operators. You can localize this, and then of course you get corresponding sheet-wide statement. Then you can define the module I plus of u, which is just the sum, formal sum of particle n plus 1 k goes from 0 to u. So this object definitely is dy module, but it also has the obvious action of particle derivative with respect to n plus first coordinate. And if we also put it I put that if I take u sits inside I plus of u and xn plus 1 on u in 0. And since the result of the relation xn plus 1 particle n plus 1 is -1, then we see that this becomes the x. And this is the special case of direct image of the X modules. And first of all, my instruction is something very close to that. So direct image, the module direct image you apply for it, there is nothing to do with all module direct image for this. They not in the case of inverse, by applying together to function, you get the same form. This is full here. And then this tells us that if I look at I plus of U and look at the curve x n plus 1, this gives me back this piece of U. So this leads us to the following definition. So let B the X module supported in Y. But because of this condition, any element of this module, if we apply sufficiently large power of X plus 1, it gets killed. So for any B in B X large. Okay, so what is the exercise is if we know by V naught the kernel of Xn plus 1 as a map from B to B, then this is clearly a Vy module, and I have an actual map with the I plus of V naught in B. And this map defines an equivalence categories of Vx modules supported on Y, taking my, so I have this V, with V modules supported on Y. For example, we send V to be 0, and I plus of V0 is V, so V naught, the inverse function. So in one direction, you go a direct image, in the opposite direction, you go by taking kernel of Xn plus 1, which is first lefty right contour of the image. So this is the exercise. Then you can easily use the compositions to consider say a k-dimensional subspace in some Cn, and then general argument if you have closed smooth subparameter Y in X, then you local define the coordinate system in which you can essentially say that. So these two pieces give us everything we used last time to classify irreducible elements. And this gave us the classification of irreducible hydrogen groups. So the question Dorothy mentioned yesterday and Steve about so one important consequence of all this, one really essential thing is that classification of irreducible Alexander shapes gives us trivial description of irreducible objects in the category. We don't understand them at this point. We have to discuss this, but say if you look at the case of highest weight category, but classification of irreducible is simple because you get it from Vernon. There is nothing like this in classical representation theory of real sense in Greek, and this was the exhausting part was really tricky. You can construct irreducible representations, very strict, but to show that you got all the strict, I mean, Archandra use, for example, to show its own strict series, he used to prove the discrete part of quantifiable form, which is required a lot of technical work, and from this he concluded that these are all discrete. You will see that from making more precise, they can improve because this, very, say, much easier fact. So I don't know. This is one important thing. I hope you agree with this, and there will be some.
I feel like we didn't. So the exercise is to show that arrow is an isomorphism.
Yeah.
And what's the relation with I upper star? Because we've already seen the functor I upper star.
This is the IL. In this case, a minus 1 I upper star is which says the.
Yeah.
Because basically you calculate it from a complex where the differential is given by multiplication by x n plus 1.
So maybe it's just important for the students to notice that from the definition of I upper star actually, like the non-derived version just gives 0. No?
Yeah, exactly.
Because
exactly. Yeah. So.
And this is more maybe, I don't know, this is like that V0 is what abstract geometers would call local model.
Yeah. Yeah. So now another thing, I mean, the is, I wouldn't call it an exercise, requires a lot of things, but say for graduate students, you can describe this and do it to help them, is understanding how to generalize this sketch here to definition of a direct image for an arbitrary morphism. So what I want to discuss is the general notion of direct image. Because I don't think except my notes that this is very place where this is really explaining detail. There was a bunch of errors in the book. I don't think it's at the end. So let me just go through this. This is like a series of exercises, and then when we get done with this, we can actually use work.
Dragan, can I just bang on for one more second? I'm not sure if it's useful or not for students, but like if you look at that picture over there, so Kashiwara's equivalent says that D modules on this line is the same thing as D modules. So D modules supported on this line is the same thing as D modules just on this other space. But somehow this is a very non-trivial equivalence. Like the D modules themselves look very different under these two incarnations.
Yes.
So you kind of spit off these normal directions.
But I think the only, if you are an analyst, this is not very surprising because distributions on the big let's assume now that we are correct. Big manifold supported on a submanifold are obtained by taking distributions from submanifold and applying normal derivatives. So there is
so you're saying that like
Uh,
if I take the Dirac delta at 0, I don't just get Dirac delta, but I get all of its derivatives.
yes,
All of these are
exactly, exactly. So this is another good model to think about direct image coordinates, derivatives of Dirac.
That's super nice. I never thought of that.
Yeah, I this, or you can look at translating Laurent series. So there are all these models which are useful to kind of predict what's going on.
Wait, sorry, I want to understand that better. So
Yeah,
you're saying that you should say it again. So you said you take all normal derivatives, you want to take distributions submanifold.
yeah.
You take all normal derivatives of what?
I mean, there is a theorem saying Schwartz book that if you have this situation, you have a smooth manifold and a closed manifold and closed submanifold, then the distributions on big manifold supported on the submanifold are obtained by taking this genuine distributions on submanifold and applying normal derivatives, making linear conditions.
Like just in a very simple example, there's only one distribution on a point. But now you include that point inside C, and then you have Dirac, but you've also got all of the derivatives of Dirac, and there's no, the kth derivative of Dirac is never 0. So you spit out infinitely many distributions which are in this one distribution.
The point is you can take a function. First, differentiate it as much as you want in the normal derivatives, and only afterwards restrict. And then apply this.
Because if you distributions are linear forms, so you can take smooth functions on a big manifold, restrict them, and you get compactly supported smooth functions on small submanifold. You can apply distribution on small submanifold and this, but then if you differentiate, you get on a big thing, you get different distributions, and this is an algebraic sum of all this dependent in the order of the normal derivative. So this one is, I need to do the calculations by S. Verb modulus for SM2 is just standard thing going up and down. But so that the proof of the theorem is really elementary, but it's very far-reaching. Yes, and another thing I forgot before this dimension. If you think about this, you see that this functor also preserves finite generation. So if you localize this, it will preserve coherence of U modules. So you can calculate characteristic variety for U0 and U1, and this is the part of the exercise to figure out how they are related. But from this, you see that the dimension of characteristic variety plus of U is equal to the dimension of characteristic variety U plus 4. So one of these guys is going on, the other one is going on. So I plus preserved. And this is everything I used last time. Okay, so now we can go to, okay, further. So let's consider part is very amorphous and smooth, right? Then we can take y and we can take the sheet theoretic residual of y and the old logical inverse image is just x tensor f inverse y. So this is
weird.
right.
Dragan. This is weird. Isn't it F upper star? F upper star.
You know what?
F upper star, I think.
And yes.
A very good read.
Yeah. Right. F inverse y. But also as a natural structure of let Ex much. Okay, so I want to explain this and this way. So this object as a binomial is denoted B X Y because it's given. So let me just point out this is true in the simple example that take x to be C n and y is m and f is the polynomial map from C n to C. Then, if you look at local sections, the dxy is just a tensor product of regular functions of x over regular functions of y. Here, the multiplication by pulling back regular functions. So that's simple. And of course, this is right dy or the right multiplication y, but you can define the action of the effects in this by defining particle that are particle P or P's of polynomial S is equal to the derivative of P in respect to x tensor P plus the sum J goes 1 to 6. And P partial y I equals f. So this is I over respect to let's see if I did this up. J X I tensor the partial respect to y J. So one can easily check that this gives the action of E of x, the left action E of x, which commutes commutation with columns in providing Dy action and also in one check. More carefully, one can see that the image of the action of E of x is just the all differential and morphism of this RFX module, which commutes with the right action required. So this can be done in general.
Dragan, so this is like fancy training, right?
Yes, yes. So I wanted to write it in this way. I mean, this is how Bernstein introduced it in his original paper because I think it's easier to check everything. In general, you have to show. I mean, look at the differential of the map and show that this is it doesn't depend on the choice of coordinates. Kind of method that's very world. So at the end, you show that this dxy, which is a left the x and right f inverse y. So this is this y module, which is like a change of rate thing. If you look, say, at the inverse image we discussed, I don't know if you pointed out this formula, but let me just briefly point this out. We did. So I am looking now, inverse image at a some u, which is the dy module, and we do the x y tensor with f inverse b y f inverse of u, and this becomes the x module, and this is the inverse module. But in this case, you could try to decipher this, and this is equal at upper star of okay, let me write down. F upper star of y is all x tensor f inverse y with f inverse dy tensor with f inverse dy with f inverse of u. So these guys, I have to it, they cancel, and we see that if we forget the Riemann construction, it's just the inverse image of. So here, nothing exciting happens except that this bi-module gives you the natural action of the inverse. But in the case of direct image, things will really bad. And then this is the main point. Careful, because again, we use the same bi-module tree. So let's say V is the X module. So now we have to multiply the dxy from both sides. So I will say that this is right. And then we are going to discuss the left or right. If I have this, I can take V tensor over d of x with d x y. And what I get is f inverse dy. Of course, it's on a wrong space. So the first idea is just to take the theoretic image. I mean, unfortunately, this does not work. I mean, it works. You get it fine the curve. But since this guy has the f inverse dy module, we have no idea how to all about this structure. Definitely, we cannot talk about quasi-coherence. It's just a sheaf of algebras. So, for example, if your V is quasi-coherent d of x module, you apply this functor, you have no idea what you get actually. The other thing is, more, then this functor, if you apply to the format F and follow G and look at composition, you don't get the same result. So definitely this is wrong. So, and the reason for this is the fact that this is a left exact and this guy is a right exact. So what you have to do is to take the corresponding right functors. So you direct image makes sense for general models, since you have to set it up and derive it. So this is the first observation.
And Dragan, so this is an f lower star f upper f minus 1 dy module, but then I have a map from dy to that given by the adjunction. I don't think you explained yet why this is a dy module.
Why this is
a dy module?
Oh, because of this adjunction here. Yeah. Yes. Yes. I mean, the problem there was that f inverse was pulled twice, so you had to push it back and then use it.
And for the younger members of the audience, mixing R and L is not going to be done.
Yes. Yes. So this is a big ideological battle. When the leaning insists when you deal with derived categories that use R's, eliminate functor is the derived. So if you read this stuff, be very careful what the notation. Okay, so now I mean, if you listen carefully, you see that I am putting something under the rock. I have to tell you what. See, but in this discussion, when we were discussing the question to make sense of the formula, I have to forget quasi coherence and just talk about sheaves. So sheaves of dy modules. So I have to consider. Yeah.
And this is the train of thought. What is this coming to?
Therefore, inverse image nothing exciting as it's just This is our marginal inverse image. And if you forget the leaf structure, then it's just the old marginal inverse.
Oh, you think as an open concept?
Yes.
The
Yes. Forget the marginal structure, it becomes the same thing as inverse image of both modules, so we know that quasi-coherence is preserved. Yeah, so here there is nothing to worry.
And maybe just another philosophical point, which is that like in non-commutative algebras, functions are often given by bimodules. And
Yeah,
we're saying
yes, yeah, this is another thing we are going to discuss.
That you can say, okay, if we are not finding your eyes, so let's see, maybe when Jordan mentioned this, let's before the break, let's discuss this, because this will appear later in the discussion. So let's assume that X and Y are smooth. Alpha and right. Then I have this is now a genuine bimodal X Y. It's like the Y left the X. Where these are global. Now I'm looking at global settings. So then, if I take, say, for inverse lineage again, I'll have the X Y tensor over dy with say u. This is dy. So this is change of rings. The other one is say v tensor over dx with dx y. This is directed. Take a dx module and tensor with this guy and then dy module. So for affine varieties, both functors are just change of ring functors given by tensor. So they have left dy. But this guy here, because of this, will not be neither in general, neither right or left line. For emergence, direct image, higher direct image is right line functors 0. So basically, one has to use the right categories to discuss this. So let's see, how far are you from the break?
It's a good place to stop for the break.
Yeah, because
Let me just point out, so what we want to, and here I describe the functors for affine varieties for global sections. I can sheetify these U's and V's, and I get positive coherent P modules on these affine varieties. And I want for those, of course, that these formulas hold. And so I have to show that actually this formula works in this, and that in general, if I take a complex with quasi-coherent cohomology and apply direct image, I will get the complex with quasi-coherent. And then, of course, you can say, but how this all fits with the right category of quasi-coherent models. This is another part of the story that I'm going to discuss.
Maybe an exercise I should do is take y to be a point p.
Yeah, we are going to do something very similar. Yeah, a fun way of looking at this is your problem is using Weil algebras and doing formal Fourier transform. Then this becomes the exercise we just discussed with multiplication with X. Yeah, I mean, there are some tricks. Well, I mean, Weil algebras is so nice, proving some properties of modules using, say, this formal Fourier form become very slick. So, of course, in general, it's breaks down. One can, by some effort, one can extend those to work in general by using Kashiwara and embedding local physics. Now there is this general nonsense. So we can consider for the moment categories of okay, I skipped one thing about this. But I will discuss it today. So we can look at the categories of D modules and the category of Y modules without quasi-coherence assumption. And then we define our contour by the form y ways. And this makes so I take the derived categories and on the derived category. And in this case, I can define at lower plus by this formula, which is F plus applying some complex V of right the X modules. Over the star. And everything is fine. We get the contour here, and then we can check the following properties. First, if I have F from X to Y and G from Y to Z, then you can show that if I apply directly respect to that, and then directly respect to B, that is the B. And this uses something called product formula. If you look at Archon or EGA, there is some this which if you write out formulas, it allows you to switch the order of historically direct images from this default. There is infinite telephone. This is the best thing. Like so. And then also you can check that okay, so another important thing to start this is if you look at this at the board, then you see the right categories of these guys, but we are interested in
subcategories of water human models inside. So this is our objects we are interested in, and we know how to deal with them. We don't know anything about these guys. So we can always consider the derived category of EX functions. This is the derived category of this guy. And there is a natural function from this category just by extending the complex to complex curve in the bounded category of all the effects modules with, say, quasi coherence homology. So these are complexes of arbitrary effects modules by the homology spider here. And there is an obvious boundary there. Coherent complex with homologies.
When you wrote DV, DX, you just meant the direct category of DX.
Yes, oh, yes. I mean, this was our short thing. Let's make this.
I just missed that.
Yeah, I mean, in all previous discussions that I was not considering at all.
Yes.
At least. And then the statement is that this is the equivalence of so this is, I think, discussing this was an error in Borel's original version on the manuscript. We had a seminar at the Institute, and on these things that Borel was writing the book, and I told him that this is not clear. I mean, it was related to the definition directly, which he has very done, and said yes. But this must be true. And then he said the proof must be the same as an partial for phonics, or partial and same thing. I mean, the statement is a little bit delicate. It works for almost so for the variance. So it's not something straightforward. And then that's something that I never forget. This is true. I told him that Harsham's argument cannot work because it uses commutativity. This is in residues and duality. You check. There is no chance you can extend this. And check. And yes, it's really that. But this result might be true. And it said, maybe nobody thought, maybe nobody tried to find the proof of it, but it has to be true. And for that, let through the roof. But so much time writing it now. So after some time, Bernstein produced a proof, and actually, then I found that in SGA there is an article of Verdier, where he constructs the functor called coherent. So you have forgetful functor here, and there is a functor going in opposite direction called coherent, which say when affine variety is the thing
is kind of obvious that you take all sections of the sheet and then you open it. And in general, you do something like check resolution. And this is how you show it through on this pattern. So basically, the idea is that if you prove that this factor preserves quasi coherence, then you can start with this category and use this equivalence. On this one, you have the definition of the direct image, and then you end up in here, then for homologies here, and then you use the equivalence to get the contour to go to the spot. So this gives you the contour between the right categories was here. So how do you?
Dragan, maybe it's what, like, one has a very similar problem for derived categories for constructible sheets. Where, when people say DVCX, they don't mean the derived category of constructible sheets, they mean the derived category of all sheets whose cohomology sheets are.
Yes, yes. Yes.
There it is.
Well, no, they're the same, if you're allowed to arbitrarily define what that. For each clarification, absolutely.
So, you rejected the certain demon, like GK.
No, I mean this. No, this is completely why in this case. I mean, the thing is.
No, like, imagine that I, like on P1, I say derived category of D modules, which are coherent with OX modules.
Yeah.
That would not be the same as the right hand side.
I mean, coherent was it?
So, like, literally, like, I'm just saying, like, is a local system.
Okay.
The left hand side would be
Yes, if you put coherent here, then you have the coherent over here.
yeah, but the X, like the left hand side gives you derived category vector spaces, but the right hand side there's an X2 corresponding to the cohomology of P1 or something. So you fix your stratification, the same issue as with D modules.
I mean, you see, in a way, since when you do calculations, you basically quasi coherent modules, you basically reduce calculation to this. Basically, these are things you know how to calculate with modules. So you have to get out of, you have to be quasi coherent sheets. I mean, there will be these examples soon. So with this observation, you check, first of all, you can prove that quasi-coherence is preserved, since this is the local property, you can always assume that Y is something. They can always set around the point and pull it back. And then you, instead of a module in D of X, you replace it by its check resolution. And since, I mean, to check that if F is open embedding, then F lower plus is F lower dot sheet theoretically direct image. So in pieces of check resolution, everything reduces to this statement. So if you know that this functor is the same as this on quadratic view, that everything follows some standard tricks doing action in the length. So in my demon models, this is divided.
A derived tensor product.
I was, okay, this is it. Where you have to change your breathing and if you want to divide the function, then you have to take, but both directly and inverse each other, derived functions.
But I think Dragan's point here was you just need left to right, you don't need right and.
Oh, yeah. So these are this one can handle with, say, old-fashioned homological algebra. I mean, this guy.
Oh, so you can just write tensor product, and then if you want to take higher.
Yeah, if you need higher. Oh,
Yeah.
so when we started learning this, then Clemens was who hated formalism. You all wanted to do everything with spectral sequence. We had a long ideological that it does not work at the end. And it took a long time to convince him that spectral sequence is relevant. Okay, so this is the rough sketch how to deal with this. Now, assuming that we have directly discuss something else that is equivalent of derived patterns. So if you look at there's another thing that I think in, if I remember correctly, George's notes, he discussed this left and right.
Chris did.
Chris, okay. So this tells us, if you look at this multiplying a 3x module, like a bundle gives a right module. So if you interpret this, this actually implies that dx small is the same isomorphic to d omega x. So this is canonical bundle. So this tells us, I mean, if you just think about this implies that if D is the twisted sheet of E modules of this sheet of different operators, then D all is the twisted sheet. So if you have constructed for twisted sheets, then you don't care about left and right.
And it is also.
One has to be careful how to define this twisted sheet and so on. You usually do something like this, and you say B. Tensor with line bundle with OX, and this is being final. This is right. And here taking parental. And then this is all of the community.
things better construction.
Yeah, because it's clear what's going on. We're using the B, and this is still what we want. This is B phase listed by L. And then again, for B module pointer is just multiplying with this phi module. If you want to. So basically, you use, if you study direct images, its notation is simpler if you deal with right modules. Inside those paper of ortho modules, he deals with, or this with right. And another related thing is if you have a this B, say on Y, twist the sheet with differential operators, and we take F from X, then you can look at a construction of B X, Y. This is of course right. But if you look at the differential and the morphisms on this one from the left, when you do this right action, you get something of this veto differential operators X. But this twist on B induces the twist of X. So you will get here some twisted B of X. So you can pull the twist back to X, and then you define the direct image and inverse image using the file. So in a way, the target drive the twist induces twist on the starting. So this is in our construction. Okay, so now we get to the back to representations. So if we take the category of, say, the lambda modules, the right category of the modules, and the right category of the data modules, then of course, bound to the right categories that are gamma. Then you can show that homological dimension of U data is finite if, I mean, there is a precise bound if theta is regular. It's infinite if theta is singular. So singular case issue, but if theta is regular, then we can also derive factor of local integration.
Dragan, I forgot how one shows that.
What?
I forgot how one shows that.
This thing,
The finite homologic dimension.
you use the factor D modules that you know bound.
Oh,
It's in my notes, and then you use local to global.
This is not so not an algebraic.
Yeah, no, this follows, at least the only proof I know is. Yeah. Well, actually, I know for this, because this is something acted like proof. And there you construct a module with where there are infinite many things. So this definitely it reduces in a way to the fact about law using very general and all kinds of organization.
What do you mean that you produce a module
In the derived organization.
Oh, you just put it literally.
Yeah, because you see I do not remember the details, but we are going to discuss this intertwining functors, which basically fully fund if you want on the intertwining functor takes one B module and produces a B module with the same module. And if you iterate this, you get, I mean, and interpret this in terms of derived organization, that you see that this thing cannot be bounded from this. Very,
So the fact that you stated in finite multiple dimensions not. So
I don't think
it's wow.
I mean, it's in my notes. I think the paper is in proceedings. So, if the orbit is regular, then this makes perfect sense. And these are two arguing functors between the right categories. And if you look at one situation, I mean, here you can represent any you say like any complex, bounded complex consisting of projectives. You send it here, you use you tensor by d lambdas, and then you can show the localization of the elements of the complex are acyclic for gamma. Because for free, I mean, higher homology is belong to that. So from this, it follows, so you get it one item is more than, and then for the other one, you have to work more and control these equivalences of categories. So basically, you draw on the equivalence, then you just the equivalence of categories works on the level of the right categories. So you can always do the following. You can take a category, say D lambda, for some lambda. You can apply R gamma, and you go to DB. And then you can localize at some W lambda. And this is an equivalence of derived categories. This is an equivalence of derived categories. So you know that this is there is a functor from here to here. Equivalence of categories. And I mean, if lambda is integral, then you can hold that this will have something to do with twisting, but of course this is true in some special cases, but not normally not. So this is something quite different. And the point is that this functor can be described geometrically with intertwining functors. So the fact now it is like 55 generalization of intertwining operators, which real sensing groups.
So let's. So what I want to
Show you how you can get from one situation to the other using norm. So let's look at the two topics of plasma. And it with an actual action G, E is in the and this is the action factor G X, the Y is E of X G. And the first thing is describe the orbits of this. And first of all, we are going to say, if I take a pair of points X and Y, then they correspond to two more elements, Bx and By, and I can intersect them, and inside them I can take a common Cartesian sublogic. Now you will see why this business of specialization is useful. Because if I look at my abstract, let's say dual abstract Cartesian, then there is this specialization map to the dual of this Cartesian C, which corresponds with point X. And there is also specialization from H star corresponding to Y. And they preserve root system, so this composition is an automorphism of the root system actually given by the value of their element. Think about this, but basically you have common Cartesian and you take two different systems of positive roots, so we have some value here. And in this case, we say if this pair determines some W, we say that X and Y are in relative position. And let CW be the set of all elements X, Y, where Bx and Y are relative. This is the first part of the exercise. And the thing is that W and W and CW in X cross X is bijection. I mean, these are here. This is clear, and this is the bijection of the elements W in G orbits. So if I take a W in X cross X, then I can look at the following diagram. So first I have projection to the first coordinate, Y variety, and then I have the projections to the second coordinate, Y variety. This contains W, and I can take a Newton composition. This. So I have this smooth variety W in X cross X, which project tax or restriction on both areas. And now, over the yes. You take, say, a complex of models. And you pull it by 5 2. So you take it into the scene, and then you transfer. Now you did sort of the line on the PW, where PW is the inverse image on P1 of O W rho minus rho. Rho is half some positivities. So this is the V module on PW, and then we take the direct image with respect to P1. And I mean, this thing is set up in such a way that this is in EV of the
And all functions are derived like it.
what?
All functions are derived.
Yes, yes. Everything is derived. So, and then, so this is the functor from EV V1 into the other one. And of course, this requires work, but this turns out to be a left derived functor of some functor IW. And this is probably right. So, under some possibility conditions, this factor, I mean, we have to assume something lambda with respect to W. This is the factor which corresponds to this. I will say more precisely what this thing is next time. But we point out that because this is useful in calculation, that both projections are affine points. So this simplifies the discussion, and I think this is one of the factors which lets you establish it. So in this situation, the relationship quasi-coherent general becomes important. So let's see. I will say why they are important, and I will, for example, what is the intertwining functor? I will discuss it next time. What is it doing to line bundles? It's taking line bundle, shifting because of this guy, shifting the parameter from O lambda plus rho into O W lambda plus rho, but it's also moving it in degree to the left. I'm going to that. So that when we apply homology, this P1 is anti-dominant compensate for the fact that higher homologies that's fine representation. But because of our setup, of some formal properties. So first of all, that LIW of V dot new is LIW V dot W new. So basically, the intertwining functor commutes with the shifts by waves. And the second statement is that if W is equal W prime times W two primes, and the lengths add up, LW is equal. Then the intertwining functor is the composition of the we have a product of it. So basically, using the expression, the calculation of the intertwining functors with simple roots. And also the left homological dimension of W is less than what we call this with okay, maybe there is a formula I will discuss next time because I want to move it down. Showing that this is really some fiction that if I take intertwining functor and apply to the localization or localization, that this is localization that W long time. But this falls under standard condition of lambda or lambda. It's weaker condition. That's for lambda anti-lambda. This works for all levels. So basically, the point is that intertwining functors give you a way to calculate the other localizations, say from one localization down to one situation. So this strategy is in a lot of groups that try to find you have order widely possible optimizations of them. And then you try to find one for which it's easy to prove to. And then you say by either using some trickery and by intertwining functors or by something else, say, okay, I will prove the statement for that localization, and then this will give you some result about representation. For example, there is a result of an old result of Milicic about irreducibility of principal series representations for arbitrary. And it had conditions for all roots was kind of strange. That all roots entered the game, and it worked for all regular one. And it was known that it fails for singular one. And then our idea was that, I mean, this must be the demodular theorem. And actually, for the demodular theorem, we can prove about the reducibility of standard or general increase. There's the regularity condition drops out, and you just have some condition with respect to all groups. And it's easy to understand this because basically you take a standard or general group and you move it around until your root becomes a simple root. When it's simple root, then you can fiber your flag variety or flag variety corresponding to the paradox, actually simple root, and your fiber says two, and everything, the result comes out from this two. So this is one useful trick when this machine group. Okay, I think now my time is up.
2 minutes over time.
Oh, sorry.
Fine.
So next time I will give to. Any questions?